Hello and welcome to another session on information retrieval. Let's get a little deeper into indexing today. So let me refresh your memories. We are working in a setting where there is a query. We are building a retrieval system and we want to convert the documents into an inverted index form so that the querying can be effective or faster, let's say. So how to index? So that's the fundamental question. I hope you are familiar with this character from the Tintin comics, Captain Haddock. Um, okay, so let's get to the subject. So how to index? Pretty simple, isn't it? So take any document, just tokenize, sort, and prepare the postings list. That's all, isn't it? Well, then the question arises as to what is a document in fact. Some systems store a single email in multiple files, so is each file a document? Or some files can contain multiple documents, as in, let's say, a zip file. So first of all, we need to understand what a document is to us, and this depends on the task at hand, the kind of retrieval system that we are building, or the domain to which we belong to, and so on. Okay, so the first step is usually deciding what a document is, and once we have done that, it seems like you could take a document, tokenize it, sort, and prepare the postings list, isn't it? Well, it turns out that there are more challenges. So let's consider the idea of tokens. A token is a sequence of characters that make a semantic unit. So usually these are delimited by space uh, in English, but this need not be the case all the time. So let's take this example. We have a sentence here: friends, Romans, countrymen, lend me your ears. Now what do I do here? So I could drop all the punctuations and then I could tokenize delimited by space. So if I do this, I would get something like this. So I have token 1, which is friends, token 2, which is Romans, and so on. So let's say all these are queryable terms. Then I would like to index all of these. Now I could index uh, the tokens that I arrived in this manner. So here there may be some terms or some tokens which may not be of interest in querying. So let's say words like the, and, which we call as stop words. So if we are not interested in such words, we don't index them, so they don't become terms at all. Okay, so here is an example. O'Neill can't study. How would you tokenize this sentence? Well, if we remove all the punctuations and replace them with a space, we would probably get these tokens: O, Neil, can, T, study. Well, that doesn't make much sense, isn't it? So probably we need to add some more English knowledge that we have to split it in a different way. Let's say in this case, O, Neil can't study. So I got can't as a single word in this case, a single term in this case, but I really don't know whether O and Neil should be separate like this. Probably not, right? So there are many ways in which we can tokenize, and what is the best way to tokenize again requires some expert knowledge of the domain. Okay, so let's revise. So if we know what a document is and if we know how to tokenize it, then we could take a document, tokenize it, then sort the terms, prepare the postings list. That's all. Or probably not. So here is another example. Yeah, so we discussed this already. So we might want to remove some stop words from the list that we tokenize. So let's remove the stop words. Okay, so if we know what a document is, if we know how to tokenize it, if we prepare a stop words list, I mean, we should know what the stop words are. So someone has to give us the list. Again, that might be domain dependent. A finance stop list might not be the same as a sports stop words list. Okay, so this is highly domain dependent as well. Okay, once we have done this, then we could take the document, tokenize it, remove the stop words, sort, and then prepare the postings list. Looks simple here. Well, but then uh, um, there are more challenges. For example, some words might appear differently in the query and in the document, but we might still want them to match. For example, case folding. So we want to make whether the first letter of window is in small caps or big, or in a large cap format should not really matter while matching, right? So we call the process of converting everything to a single case as a small case as case folding. So that's something we could do. We could make the singular and plural forms also to point to one normalized case. That's another example of mapping all these terms to a single equivalence class, as in this example. The use of hyphens could also not matter probably to our users. Again, so these are all domain dependent stuff, but I'm taking a general search example where some users might just type anti-theft for anti-hyphen theft, and some might put the hyphens. So irrespective of whether the hyphens exist, you probably expect Google to come back with the same query results. So we would like to put these also in the same equivalence class as anti-theft. And note the differences in spellings depending on which variant of English you speak. Again, so in this case, we have color and color with a U, both mapping to the same equivalence class. So the class to which they map to doesn't probably matter as much as long as we have the right equivalence classes defined. Okay, so that's token normalization for us. So here what we are saying is that if there is a query, so let me get my pen here. Okay, so if I have, where is my pen? Yeah. So if I have a query, what I would do is normalize the query terms. So let's say I get a normalized form of my query. Now I can match the normalized form of query with my index. So let's say this is my retrieval system, and let's say there is my index. So in my index, so I have the dictionary, and then I have my postings list. So here I could have the normalized form. So if irrespective of whether the query contains window or window, the normalized form would just have window in it. So we reformulate the query and we match the normalized form to the dictionary, and thus both these queries would match and produce the same uh, results. Okay, so that's normalization, but usually normalization is a challenge because cat and cat might be very different, as in a common admissions test could be an abbreviation for CAT and not the animal cat. So how do we distinguish these things? So that's usually a challenge. There could be many different examples. Bush may be in the name of a person. Need to be careful with proper nouns. Also, we have to decide what kind of normalization is appropriate for a situation. So true casing is simply leaving, not converting all the letters to a small case or a bigger case. And just converting words at the beginning of a sentence to lowercase, leave the rest capitalized, for instance. So these are some ways, but then which is the right way largely depends on the domain. So these challenges make searching quite complicated because preparing a good index is the first step for effective search. Well, the simple answer seems to be just lowercase everything. That should work fine in most cases. That's what we have seen in many of the search challenges out there, but we really don't know if some other way is more effective. Okay, so there are two other commonly applied techniques. They are stemming and lemmatization. Stemming refers to chopping the ends. For example, if I have going, I just chop it to go, and removing such suffixes might lead us to a form which looks normalized. But remember, this need not result always in a dictionary word. For example, if you take analysis and if you give it to a stemmer, it would give you analyze, and this is also what it would give for other forms of analysis. For example, analyzing, 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 and many other forms. So we'll probably get this form, which works in most cases. Yeah. There is also another way called lemmatization, where we are interested in getting a dictionary form of the mapping. So, for example, if you take saw, we are not interested in only chopping a suffix of saw, but we want to convert it to a known dictionary form. Let's say C. So, whether the input is C or saw, I would get C as the output. So that's lemmatization. There are many more examples of lemmatization. So am or is get converted to b, and cars should get converted to car. Similarly, we have democrat, democratic, and so on getting converted to democrat. So these are just a few examples of lemmatization. There are well-established lemmatizers and stemmers out there. One of them is Porter stemmer, which is quite popular. We would not get into the details of the stemming algorithm used by the Porter stemmer, but I would try to give you an intuition of how it works. So it applies several phases, and it is rule-based. So it takes the input and starts refining it. For example, let's say the first rule is SSES to SS. So what does that mean? So whenever you have SSES in suffix, just convert it to SS. So that's what the rule says. So Karasis would just become Karas. Yeah. And similarly, ponies, IES, convert all IES to just I. So that's another rule. So IES becomes just I, so leaving ponies to just pony, right? And while we are applying these rules, so here is just an identity rule. So if you find SS, just leave it as SS. Don't do anything to it. Let's look at this interesting rule. So if you have S at the end, then just remove it. So cats become cat. Okay. So if okay, there are some rules which use an interesting measure called the word measure M. This M refers to word measure. So it simply says that if M is greater than 1, then apply this rule, which simply removes EMENT from the suffix. So EMENT from the suffix should be removed only if the prefix length is more than 1, right? So this rule does not apply to cement, but is applies to replacement. There are many such rules. We would not get into the details in this course, but the interesting to note is that this algorithm is simply rule based, and it goes through certain rules in a particular order and then applies another set of rules as part of the second phase, and then another set of rules as part of the third phase, and so on. Uh, and that's the reason why you might sometimes end up in a non-dictionary word when you are applying a stemmer. A lemmatizer, on the other hand, would always lead to a dictionary word. There are many stemmers out there: Lovin stemmer, Pace stemmer, and if you apply these stemmers on the same text, you would get very different results, and that's because the rules that they apply are different. The algorithms they use are different. So here is just an example of what happens if you give the same text to Portal, Lovins, and Pace. Well, it's hard to come up with one universal stemming algorithm which works for everyone. So stemmers are not perfect. So these stemmers go through two major problems, one called the overstemming problem and the other the understemming problem. Um, let's take the overstemming example. We end up cutting too many characters that two different words become the same after stemming. For example, university and universal are two different words. They should not stem to the same output, but unfortunately they do when we apply the common rules of stemming. So university and universal both lead to universe, which is bad. We don't want to match the query university to documents that contain universal. On the other hand, we might also end up in the understemming case. So take this example of data getting converted to dat and datum getting converted to dat2. We would ideally like data and datum to both stem to the same result, but in this case, they are stemming to different results. Ideally, we would like the results to be the same. Okay, so what have we learned so far? First, we have to decide what a document is. Then we need to know how to tokenize it. Then we need to know what a stop words list must be. And if we are successful in doing all these, then we could take the document, we could tokenize them, we should then normalize it. We should remove the stop words, we should stem or lemmatize it, we should sort it, we should then prepare the postings list. That's all, isn't it? Uh, Indexing is not easy, and these are the reasons why indexing is pretty challenging. Well, if the challenges are even more, for example, here is the Korean word as I learn it. I mean, I'm I'm not a Korean. I don't know Korean, but I understand that this means nice to meet you. Now there are no spaces here. How would you chop it? Um, Take another compound word. So these are called compound words. This is a German compound word for Federal Education and Training Act. What would you do to tokenize these kind of words? Yeah, so there have been a lot of research on these lines to understand how to do the stemming, how to do tokenization in these cases, which is beyond the scope of this course, but I just want to convey the message that even the simplest uh, of the tasks in information retrieval can be really challenging in the real world. Um, Even if there are white spaces, there are many cases where splitting with white space can lead to really bad results. Can you think of one such case? Please pause the video here and think of a case where there exists a white space, but if you split it with white space, then you end up in a completely different semantic unit, which is not worth indexing. Here are some examples. New Delhi, IT park, so there's no point in matching new, the word new. If you're querying for New Delhi, you don't expect documents that contain new in it. You want documents that contain both new and Delhi in it. So know that always splitting with white space also does not work. So the point here is that indexing is a very challenging task. There's a lot of research going on in the world of indexing. All that we have managed to understand is that this is a highly domain dependent work, and and seemingly simple tasks can be quite challenging. Look forward to see you again. Till then, thank you.